This is question D5.5 on IsaacPhysics. Reading the question, we have two waves of amplitude 4 centimeters and frequency 14 hertz, moving in opposite directions at 5.6 meters per second. So I know the frequency is 14 hertz, and I know the wave speed is 5.6 meters per second. If a standing wave were formed, how far apart would you expect the antinodes to be from the nodes on either side of them? So because this is a standing wave on a stretched string, then I know it's going to have two nodes at either end. Now it might look like that, or it might look like that. I don't know how many wavelengths worth are in it, but I know it will have two fixed ends, and those ends, because they don't move, are therefore nodes. The points where there is maximum amplitude, so there, or on a different wave depending on how many wavelengths fit in, would be there. They would be the antinodes. So I'm looking for the distance between node and antinode. To work out the distance between a node and an antinode, I first need to work out the distance of one wavelength, and then I can work out the node to antinode distance. I can work out that distance once I know this distance. To work out the wavelength, I'm going to use the wave equation, rearrange that for wavelength, and I get V over F. Sub in my values for V and F, and I get 5.6 over 14, and that leaves me with 0.40 meters. Because I can see that within one wavelength, there are 4 node to antinode distances, I would go 1, 2, 3, 4. Then that means the distance, if this distance is 0.4, this distance is a quarter of that. So if the wavelength was 0.4, then it means the distance from node to antinode is going to be 0.4 over 4, so it's 0.10. For part B, if the string had two fixed ends, aka nodes, what is the minimum length it must be in order for a standing wave to be possible? So to get a standing wave on your bit of string, you would want to have the fundamental frequency one that looks like this, where you've just got one antinode, because that means you don't need to fit in loads more antinodes. So that'd be the shortest possible bit of string you could have. So let's work out that length now. You can see this represents one wavelength, so this would represent half a wavelength. We just calculated in the previous part that a wavelength is 0.4 meters. Therefore, the length of this bit of string is half a wavelength, so it's going to be 0.4 over 2 equals 0.20 meters. Part C of D5.5 says if the string had two fixed ends and was 0.7 meters long, why would no standing wave be formed? Well, it's because the internodal distance, which means the distance between two nodes, is 0.2 meters. We just saw that on the previous part we just did. If the distance between two nodes, bits that don't move, is 0.2 meters, then you can't have a bit of string that's 0.7 meters long, because this number does not divide into this one, so it won't work.